you for the final lecture.
Okay. So finally, hybrid zones. So let me begin by telling you what a hybrid zone is. So a hybrid zone is when two genetically distinct populations come close together and they hybridize to produce offspring of mixed ancestry. And what we observe is very often that these hybrid zones are maintained as being really quite narrow. So the picture here is Antirrhinum in the Pyrenees, so the border essentially between France and Spain. And what we've got is in very narrow bands, just a couple of kilometers wide, we see on one side, the population is entirely these yellow flowers. And on the other side, entirely these sort of magenta colored flowers. And in the hybrid zone, we see these beautiful variants in between, such as the British grow in their gardens. And it's actually, there are many, many examples of hybrid zones. And one thing that happened was that during the last ice age, which in Europe was about 18,000 years ago, it's not as long ago as we like to think, the plants which we see now in Northern Europe retreated to refugia. And then when the ice retreated, they expanded very, very quickly. And they were in those refugia for long enough that they evolved to be genetically distinct, but not so long that they couldn't interbreed. And that's what we're seeing here. But occasionally we get selection against those hybrids. And what's believed happens with the rather beautiful hybrid flowers here is that pollinators like bees are less able to identify these mixed color flowers than the pure yellow or the pure magenta. And so they're simply less successful at reproduction. Okay, so what we're going to, there are many reasons that hybrid zones can exist. It be just because of a sharp change in the environment, but we're going to focus on hybrid zones that are maintained by genetic effects. And we're going to focus on a very simple case. I mean, you can see with the flowers, there's more than 3 different types of flower, but there aren't a huge number. And the flower color in the Antirrhinum is maintained by a fairly small number of genes. So we're going to caricature it just by looking at a single genetic locus. And here's our model. So we're going to assume what's called Hardy-Weinberg proportions, which just means that if the proportion of little a alleles across the whole population is W bar, then that's reflected in little a homozygotes. So think of that with your pure yellow flowers, say, are form W bar squared of the population, little a capital A twice W bar 1 minus W bar, and capital A 1 minus W bar squared. So equivalently, if I want to know the type of an individual in my population, I'm essentially sampling at random from the alleles that are available. And what we're going to suppose is that the homozygotes, the little a, and the capital A, are fitter than the heterozygotes, the little a, capital A. And the relative fitnesses we're taking in this way. And just as last time when I said, I'm not really telling you what relative fitness means, it means whatever my mathematical model says on the next slide. The same is true here. So during reproduction, we're going to take a slightly different angle, but again on a Wright-Fisher model. So during reproduction, what happens? Well, each heterozygote, each little a, capital A, is going to produce 1 minus S times as many germ cells. So these are cells of the same genotype as the parent, as a homozygote, as a little a, or capital A, capital A. So what happens during reproduction is that the parents produce lots and lots of germ cells, and the germ cells carry the entire genetic type of the parent. And then those germ cells split into gametes, which carry just 1 copy of the gene. So if you've got a little a, capital A germ cell, that will split into a little a gamete and a capital A gamete. Okay? And what we're supposing is that the selection is entering because the number of germ cells produced by a heterozygote is less than the number produced by a homozygote. But it's still an extremely large number. So I'm really talking 1 minus S times infinity here. I mean, very, very large numbers. So the germ cells split into this effectively infinite pool of gametes, and it's from that pool of gametes that the next generation is sampled. So if the proportion of little a alleles in my parental population was W bar, what's the proportion of little a gametes? Well, each little a homozygote necessarily produces little a gametes, so that's this W bar squared. The heterozygotes, of which there are twice 1 minus W bar, that's the probability of somebody being a heterozygote, they produce 1 minus S times as many germ cells. So that's this 1 minus S factor here. And moreover, only half of the gametes are little a and half a capital A. So the two which you'd expect to see here, it will be twice W bar 1 minus W bar, but multiplied by a half, because they're only half of their gametes are type little a. And then on the bottom, we're just normalizing. So this is the total number of gametes in the population. And you can somehow think of having infinity times the number on top and infinity times the number on the bottom, if you like. So this is just the total number produced by the little a homozygotes, the total number produced by capital A homozygotes, and this is the total of number of gametes produced by the heterozygotes. Okay, and that simplifies, of course, to this expression. And as usual, I'm going to expand that and ignore terms of order S squared. And what one can see is that W star is, which is the proportion of gametes which are of type little a, is the proportion in the parental population plus this correction. And notice now that whereas when we did genic selection in the previous lectures, SW1 minus W is always of one sign, this will now change. So the proportion of little a gametes will be bigger than in the parental population if W bar is bigger than a half. So in regions which are largely homozygous little a, I'll have even more little a homozygotes in the next generation, because they're going to be sampling, the diploid individuals are chosen just from sampling from this pool of gametes. On the other hand, in a region where there are not so many little a gametes, I'm seeing even fewer, because twice W bar minus 1 is going to be negative. I'm going to see even fewer in the next generation. So what this mechanism is doing is it's forcing the proportion of little a alleles to be closer to either 0 or 1, according to what the proportions were in the parental population. So in particular, W star minus W is given by this cubic now, SW1 minus W times twice W minus 1. Okay. Now, as usual, we're going to suppose that selection is rather weak. And in a very large population, an infinite population, if S were taken to be alpha over M for some large M, and then I measured time in units of M generations, then the change in allele frequencies over a single generation divided by the intergeneration time would take this simple form. And I could imagine that it was sensible to approximate that by an ordinary differential equation. And the classical thing to do is say, okay, well, that's a very good model. So now let's add some dispersion. And when I add dispersion, I suppose that individuals are thrown off around the parent according to a Gaussian, say, and passed to a suitable continuum limit. Then I arrive at this equation. And this equation is a very famous equation in partial differential equations. It's a special case of what's called the Allen-Cahn equation. And this model is quite widely used to model the evolution of hybrid zones. So here's a classical hybrid zone. This is the mus musculus hybrid zone, so the common house mouse. And the hybrid zone splits mice with one fur color from mice with another fur color. And it runs all the way through Europe from the sea down here near Trieste, right up through Plön in northern Germany and up through Denmark, and comes into the North Sea up here. And as you can see, it's really, it's rather regular. And it's also very narrow. I mean, compared to the range of these mice, it's a very, very narrow hybrid zone. And I emphasize that other mechanisms can lead to hybrid zones. It's not just this genetic mechanism, but we're going to focus on this genetic mechanism. And the width of the zone will be roughly square root of twice m over alpha. But when I zoom out and look at the scale of a continent, you can imagine modeling this hybrid zone as though it were a one-dimensional object. And that's really what we're going to do. Okay. So if I zoom out, if I look at that hybrid zone over very, very large time and space scales, so I take a diffusive rescaling, then what happens to the Allen-Cahn equation? Well, the Laplacian is invariant, and all I do is I pick up a 1 over epsilon squared in terms of the driving term, the potential term here. Okay, and for convenience, what I'm going to do is I'm going to set m equals 2, with apologies because you're probabilists, and so that rankles, but in order to compare to the analysis literature, we take m equals 2, so this is just a Laplacian, and alpha equals 1. And then it's well known that if I take sufficiently regular initial conditions, as epsilon goes to 0, the solution converges to the indicator function of a region whose boundary evolves according to curvature flow. And again, I'm thinking in 2 dimensions here. In higher dimensions, it would evolve according to something called mean curvature flow. So what's curvature flow? Well, curvature flow, if I take a family of smooth embeddings from the circle into R2, and I write, for the sake of argument, the inward normal vector to gamma t to be nt, and kappa to be the curvature, or in higher dimensions, the mean curvature of gamma at u, then the way that a point evolves is directly proportional to the curvature, and it moves along the inward normal. So in this example here, the curvature, roughly speaking, in 2 dimensions, you can think of as being the curvature at this point is the largest, is 1 over the largest circle, sorry, try again, 1 over the radius of the largest circle that I can fit inside here, so it just touches at this point. And the this point will move inwards at a rate proportional to 1 over that radius, whereas here, this point will move along the outwards along the radius of this circle, and it will move more slowly because the radius of this circle is larger. Now, I'm slightly concerned about time. I do have a video. Maybe I should show you a video. So let's try this one. So here, I hope you can see, I apologize for the name of this video. It was not me who chose it. So here we're starting from the Batman symbol, and we're going to allow the Batman symbol to evolve according to curvature flow. And look what happens at the bits that point inwards versus the bits that point outwards. So you see very rapidly, this object is becoming convex. And now it's this sausage shape, and all that's evolving, the sides aren't changing very much, they're essentially flat. But these points are moving inwards because the curvature is quite large there. And in a moment, it'll start to look like a circle. And when it becomes a circle, it will start to contract very, very quickly, because the smaller the circle, the higher the curvature, and the faster that point will evaporate. Okay, so hopefully that'll now zip away to a point. Okay, so that's roughly what curvature flow looks like. It tries to be regular. Let's try and get the right screen back. There we go. Okay, so here's our rather more boring picture than the Batman symbol, but this thing will be trying to evolve to be a convex shape. Now, what we're particularly interested in are things like mus musculus, where the boundary is actually going to try to be a straight line because it's connecting the sea at those 2 different points. And the curvature, it basically tries to minimize the curvature of the enclosed area, the curvature of the boundary of the enclosed area. And because we're connecting the sea at the 2 points, the enclosed area is essentially infinite. But what we're going to see is something which is becoming more and more, in the case of curvature flow, more and more like a circle. So we will focus on this kind of shape for now. Okay, now this isn't working now. Is it not working? There we go. So I can formalize the statement that as epsilon goes to 0, the solution to this equation looks more and more like curvature flow. Roughly, I take a nice smooth initial condition, and I set gamma 0, the starting point of my curvature flow, to be the level set where W0 is equal to a half. And I arrange that W0 is less than a half inside gamma and bigger than a half outside gamma. Then if epsilon is sufficiently small, it's not too hard to show. And this is a theorem due to Chen in 1992. Well, it is quite hard to show, but he showed in 1992 that in regions inside the curve, very rapidly, so there I'm taking my distance to be negative, very rapidly converge to 0. So as soon as I'm a small distance away from the boundary of this thing that's evolving to curvature, according to curvature flow, I get something that's close to 0. And outside the curve, I'm getting something that's close to 1. So the solution to my equation is in some real sense very close to the indicator function of a region whose boundary is evolving according to curvature flow. But what we were interested in was, so that's how the selection is interacting with space. But what about a population that isn't infinite density? What happens if we add noise? And there are results, for example, this result of Heire, Reiser, and Weber, which says that, so they took something which is the same equation. If you make the substitution v equals twice w minus 1, the Allen-Cahn equation becomes dv by dt is Laplacian v plus v minus v cubed. But they, instead of adding the sort of noise that we've got used to over the last few lectures of which models genetic drift, they added a mollified space-time white noise. And they showed that in 2 dimensions, if the mollifier is removed, then the solution to that equation converges to 0. So the noise just destroys the structure. You completely lose sight of curvature flow. But if simultaneously you allow the intensity of the noise to go to 0, so you remove the mollifier, but you also have the strength of the noise going to 0, which would correspond to letting our local population density go to infinity, then you recover the deterministic equation. And we were interested in doing that in a model which had a more sensible model for genetic drift. And in fact, in so doing, we thought we'd just be able to take Chen's result and perturb his proof a little bit, and it would all be straightforward. But it turned out that his result is really quite rigid to the analysis. And so what we did was we provided a probabilistic proof of Chen's result. And our probabilistic proof was sufficient to adapt it to a spatial Lambda-Fleming-Veo type model, which incorporated this kind of selection against heterozygosity. And the idea is simple. It mimics what we've done before, except that, remember, before we split events into neutral and selective, and at a selective event, we chose 2 potential parents, and only if both of them were type little a did we produce a little a offspring. Well, now what we're going to do is select 3 potential parents in order to reconstruct the right sort of selection. And we're going to choose that a little a parent, we're going to choose the parent to be type little a if the majority of those 3 individuals is type little a. So what does that mean? It means that I take w to w plus u times 1 minus w with probability w cubed plus 3w squared 1 minus w. That's the probability that the majority of types that I sample is type little a. And otherwise, I have a capital A parent, and this is the probability that the majority of types sampled is capital A. And why is that the right thing to do? Well, mathematically, at least, it's the right thing to do, because if you look at the change in the proportion of little a alleles over such a selective event, then you can calculate, well, with probability w cubed, the change is 1 minus w. I go up by 1 minus w. With probability 3w squared times 1 minus w, I go up by 1 minus w. So that's these 2 terms. And I go down by u times w with probability 1 minus w cubed if all the parents were type capital A, or 3w 1 minus w squared if all the parents were, if the majority of parents were type capital A. And if you simplify that, you see you're recovering exactly the nonlinearity that we wrote down before. Okay. So we won't dwell on that, because actually I find the proof of the deterministic case quite fun, and I wanted to show it to you. So the proof in the deterministic case is going to rest on a probabilistic representation of the solution to the Allen-Cahn equation. And that in turn rests on an object called ternary branching Brownian motion. So here's ternary branching Brownian motion. We're going to start with a single individual at time 0 in some position x, and it's going to have a lifetime which is exponentially distributed with parameter 1 over epsilon squared. During its lifetime, it follows Brownian motion. That's what this wiggly line is meant to represent. And at the end of that lifetime, it produces 3 offspring. And the picture hasn't come out terribly well, but they're meant to be 3 individuals that all branched out at this point. And the offspring go on and evolve independently of one another in the same way as the parent. So here's another branch event. At this time, this offspring branched into 3, and they evolved independently at the same way as their parent. And then we stop the process at some time in the future. Okay, so that's ternary branching Brownian motion. Individuals have independent, exponentially distributed lifetimes, at the end of which they're replaced by 3 offspring. Okay, and now we're going to adapt an idea of Delmasi, Ferrari, and Leibowitz, which was applied to interacting particle systems. And we're going to write W of t for historical ternary branching Brownian motion. So what do I mean? I mean that whole tree, not just the number of individuals at time 0 and the number at some fixed time in the future, but this whole tree is what we require. And that's what I mean by W of t here. and I'm going to define a voting procedure on W of t. So each leaf in my tree is going to vote 1 with probability W0 evaluated at wherever that leaf finds itself. Otherwise, it votes 0. Okay. And then at each branch point, as I'm going to work my way back down the tree, and at each branch point, the vote of the parent particle is going to be the majority vote of its children. Okay. And that's going to define an iterative voting procedure, which starts at the leaves, and it takes us back to the root. And I'm going to write V W0 for the vote of the root. Okay. So here's a picture. So all I've drawn in this picture, all these lines should be wiggly. They're all Brownian motions, but I've just drawn the votes at the leaves of the tree. So here, for example, these 3 leaves voted 0, 0, 1, and I trace back, and here's the first branch point. The majority of the leaves voted 0, so this parent votes 0. And then the next branch point of my tree was over here. These leaves have voted 1, 0, 1. The majority vote was 1, so this vote is a 1. Here, I've got 1, 0, 1 again, so this is a 1. Now at this point, this was a 0. On the left, I had a 0. On the right, I had a 1. So the majority was a 0. So the vote of the root was a 0. Okay. And I claim, so what I'm going to claim is that if I write W of Tx for the probability that if I start a single individual from the point x in this ternary branching Brownian motion with branching rate 1 over epsilon squared, which is what this epsilon means, then the probability that the root vote is a 1 is the solution to the Allen-Cahn equation started from W0. And to see why that's going to be true, let's look at what's happening here. Suppose that I knew at this branch point that for an individual sampled at wherever this individual is at this branch point, the probability of voting 1 was W, then the probability that the root vote is 1 is the probability that the majority vote of these parents is 1, which is W cubed plus 3W squared 1 minus W. So the change, the difference between the probability of the root vote being 1 caused by this branching event is what I see after the event, which is this W cubed plus 3W squared 1 minus W minus W. And notice that that's W, 1 minus W, twice W minus 1. Okay. So I claim that if I now add in the spatial motion, the fact that my individuals are following Brownian motion, run at rate 2, because I'm trying to be an analyst, not a probabilist, then the solution to this Allen-Cahn equation can be expressed in this way. And that gives me a really powerful tool for proving Chen's result about the convergence to curvature flow. Okay, and it reduces the problem to showing that if I start a long way outside or sufficiently far from the boundary of the region that's bounded by curvature flow, then the probability my root vote is 1 is very close to 1. And if I start inside the region, so far enough from this curve, which is following curvature flow, the probability that root vote is 1 is close to 0. And the proof goes in 2 steps, and it gets a little bit technical, but the idea is very simple. So first we prove a one-dimensional result. We show it in the case where where I work in one dimension and the initial condition is just an indicator function that x is bigger or equal to 0, so just a heavy side initial condition. And then I do a coupling of a 2-dimensional Brownian motion to the distance of a 2-dimensional Brownian motion to the boundary of this region, so this curve that's evolving according to curvature flow, with a 1-dimensional Brownian motion. And this really parallels the analytic approach where you approximate the solution of the 2-dimensional problem by a 1-dimensional standing wave. And let me just use that to show you why you might expect curvature flow. So let's suppose that we were in a region which was already a circle, and that the majority voting, so what majority voting does is it increases the bias. If all of my offspring are going to vote 1 with probability more than a half, then the chance I vote 1 with probability more than a half is even more than the probability that each of them was going to vote 1 which was already big and a half. So it's even closer to 1. So the more rounds of majority voting I take, the more likely, the more increased the bias is. So if my offspring had a left-wing bias and I follow my offspring, I'm going to have a bigger left-wing bias, and so on. Okay, and now let's think about what that means. Well, that means that if the boundary between having individuals vote 1 and vote 0 is the boundary of this circle, if I'm an individual at the point X, the point that discriminates between whether I am more likely to vote 0 or I am more likely to vote 1 is the point at which the probability that I am within this region where everybody's more likely to vote 0 is a half. So if this were just a straight line, if I were in one dimension, the probability of voting 0 being a half would correspond to being exactly at the boundary. But for two-dimensional Brownian motion, the probability started from a point X that in a small increment of time, my two-dimensional Brownian motion is outside the ball. Well, that's going to be equal a half if I look at its radial part, the probability of the radial part is bigger than R is a half. But the radial part of a two-dimensional Brownian motion is just a better process, right? And so this is going to be B delta T plus, well, it's not quite 1 over R, but over a very small time increment, if I'm close to this boundary, 1 over R and 1 over where I am, 1 over X are very close to one another. So roughly speaking, it's the probability that B delta T plus 1 over R times delta T is bigger than R. So that's the probability that B delta T is bigger than R minus 1 over R times delta T. And so that's going to be a half if I precisely choose X to be at R minus 1 over R times delta T. So you can see that the combination of the two-dimensional Brownian motion and then this voting bias means that the boundary of the region is going to move in according to, at rate 1 over R. So this is where the curvature flow comes from. And this generation of the interface emphasized comes from lots and lots of rounds of voting. Okay, and for stochastic hybrid zones, I don't want to dwell on this, but we have a dual process that looks almost exactly the same as that ternary branching Brownian motion, except that now, first of all, when we branch into free, the individuals are drawn not exactly at the point X, but from a ball around X. But again, what we're going to do is use one of these majority voting processes. So let's not dwell on this slide, but move, because I want to move on to something else. But look at what we're going to have in place of our ternary branching Brownian motion. Well, it's going to look a lot like an ancestral selection graph. So as all our selective events, we branch into three, but we might have simultaneous coalescence where we have more than one ancestral lineage affected by an event. So here I have an example of simultaneous coalescence and branching. And exactly as in the first half of the lecture, in the first lecture this morning, when we branched into two, now we're going to branch into three. And what we do with that branching and coalescing structure is we impose majority voting, exactly as we imposed majority voting on our ternary branching process. And it turns out that that is a very robust approximation. And with Freeman and Pennington, we were able to show that if there is, if the strength of selection, so the impact of our events goes to zero fast enough relative to the strength of selection, then we can recover that our hybrid zones, even with genetic drift, will still look approximately like curvature flow. So that hybrid zone that we see for our mus musculus is really evolving according to something that looks a bit like curvature flow. But that assumed that everything we've said so far assumed that the homozygotes are equally fit. The little a and capital A are equally fit. But actually, if they've been separated for long enough, it may be that the little a homozygotes have a different fitness to the capital A. So what we're going to do now is we're going to suppose that there is a distinction in fitness between the two. And what's going to happen is that our cubic, remember before when gamma was 0, this was just twice W minus 1. Now when we go through the same calculation, we will have a slight distortion of this. We will have 2 plus gamma times W minus 1. And if I take gamma to be order epsilon, so to be very small, because remember these hybrid zones, we're looking at evolution over very, very long timescales. And so if we're going to see anything interesting, if our hybrid zone is not going to have taken over all of Europe, for example, we're going to have a very small difference in fitness between little a, and capital A. But if I do that and I rescale, I get an equation of this form. So this is what happens under the diffusive rescaling. I just pick up a 1 over epsilon squared. But now, because I've taken gamma to be order epsilon, and I've rearranged things a bit for convenience, I'm going to get something, a correction of order epsilon in here. Okay. And what another student of mine, Mitch Gooding, showed in his thesis was that we can then get an analog of change result, except that instead of getting curvature flow, we get a mixture of curvature flow and constant flow. And it's only going to be defined up to some fixed time when things start going wrong because the boundary no longer behaves nicely, you get singularities developing. But what you can see is that there's going to be a critical value of the curvature, which exactly matches this constant flow. And so there is a stable solution to this equation corresponding to the boundary of a ball when nu is equal to kappa T. And so we're seeing two conflicting effects. We're seeing the selection in favor of the little a pushing the boundary of this region outwards. That's the constant flow. But we're seeing the selection against heterozygosity pushing the region inwards, and that's the curvature flow. Okay. Now, we started thinking about this in the context of when will you get a population actually invading. So when will you get a hybrid zone actually moving and invading an entire space, so the entire species range? So if I take a one-dimensional version of this equation, it has a traveling wave solution, and you can solve it exactly. This is what the traveling wave solution looks like. And so in one dimension, you can imagine that I might start from a hybrid zone. So I've got my yellow flowers on one side and my red flowers, but actually they should have been magenta, but I didn't have a magenta pen, on the other, and my hybrids in between. And the yellow flowers are slightly fitter, and over time they invade and eventually take over the whole space. But what's going to happen if I move into a two-dimensional space? And now what we're going to do is we're going to actually think about the shape of that two-dimensional space. So are we going to invade if instead of having a one-dimensional population, we've got some population evolving in two-dimensional space? And we were interested in things like what happens if that population might perhaps pass through a narrow isthmus. So it might have to pass through some sort of narrow strip to which it was adapted, and then it's then spread out again. Will it still invade? And there's a theorem due to, I should say, because you're probabilists, this is neither Nathaniel nor Julien, this is Henri Berestiki. So this is Berestiki the elder, the PDE guy, and co-authors, which says, well, it depends on the geometry of the domain. So they show that they don't take this limit of small epsilon, which we're taking, but they show that for some domains, you will indeed see what I just illustrated with my sketch of my yellow and red flowers, complete invasion, that the fitter type will just take over the entire domain. For some domains, you get partial propagation. So you'll get that the fitter type overtakes the domain in some directions, but not in other directions. And sometimes you get total blocking, that the invading population, what appears to be the fitter population, just can't expand any further. And the sort of domain where you might see that is one where things basically widen out too quickly. So here is a domain on which they particularly concentrated, where we've got this narrow isthmus, and we're going to call the diameter of that twice little r, and it opens up very rapidly. So imagine your population had to pass through a narrow strip of land and then opened up very rapidly. And then when it opens up, depending on the ratio between this small isthmus and this large isthmus, for certain parameters, you can see total blocking. Now, their results weren't terribly quantitative. So what we did was we went for a probabilistic approach based on the approach that Mitch used in his thesis. And we considered when, for this shape of domain, we would see total blocking. And what we can see, so this, I've written down a d-dimensional result here, but we're really interested in 2 dimensions. What we can see is that if the radius of the smaller domain, remember this was, this distance here is twice little r0, and the larger one is twice capital R0. Well, if I can fit a spherical shell, a hemispherical shell, between this smaller cylinder, this smaller radius and the larger radius, and that hemispherical shell itself has radius less than this critical value d minus 1 over nu. Now, if the radius is equal to d minus 1 over nu, that's what Mitch had identified as being the stable point for this mixture of curvature flow and constant flow. If I can fit in a smaller radius, then the curvature flow is going to win and my population is going to get blocked. And what we're able to show is that it wins in some very real sense, that if epsilon is small enough outside this radius, the population just doesn't make it at all, where even though within this smaller diameter, it's managed to completely populate the region. So we start with something that just looks like an indicator function. Now, if this were just a single tube, if little r0 were equal to capital R0, and this were a single tube, the population would just persist. We just have the one-dimensional solution. But because of this rapid opening out, the population gets blocked because the offspring are spread out too thinly, and that selection against heterozygotes prevents them from advancing further. Now, this is a very special domain, but our proof, being a probabilistic proof, is extremely flexible. And so actually we can prove a very, very general result. So here we've just got a population which has some sort of minimum width. And then in order to compare to another result in the PDE literature, we've taken this slightly unnatural parameterization where we've taken our domain to look like a cylinder. Again, we can work in d dimensions, but the most interesting biologically is 2 dimensions. And then we've got a essentially cylindrical domain which has a fixed tube of width h sitting in the middle, with capital H sitting, twice capital H sitting in the middle. But then around that, this little h is a positive function. And what we can show is that if capital H plus this positive function minus this quantity, which is characterized in terms of this derivative, which is really to do with an angle, as we'll see in a moment, is negative, then my population will always be blocked. It will never be able to progress all the way along the tube, even though it starts occupying the whole tube out at plus infinity. Okay, and the key to the proof is actually, so where does this strange ratio comes from? This strange ratio is understanding what a tangent to the curve h plus h looks like, and that's because an intermediate step is to show that if we had a domain which just looked like our cylinder and then opening out like a cone, if this angle alpha is such that sine alpha is bigger than the critical value, sine alpha divided by R0 is bigger than that critical value nu over d minus 1, and that's that same critical value for curvature flow to beat the constant flow, then the population gets blocked. And the expression we had is just saying that at some point, our cylinder's opening out at least as quickly as this angle alpha, and it might be opening faster still. But here we need this angle alpha to be at least, we need this intersection between the spherical shell that we're inserting and this straight line to be at least 90 degrees. So the cone has to be opening at least as fast as this angle alpha is dictating. Okay, and then we did add in noise, and I'm not going to tell you very much about noise, but we used exactly that result that I showed you in the first lecture this morning, which characterized how much noise you need before the branching is overcome by the coalescence. And we can adapt that to this setting, and we can see that if genetic drift is weak, then the spread of the favored type is blocked. Whereas if genetic drift is strong, so the population density overall is low, the favored population actually spreads across the whole domain. And that distinction between when you're weak and when you're strong is exactly analogous to the distinction that we had with genic selection as to when you were weak and when you were strong. And again, it's really reflecting the fact that selection is more effective in larger populations. So it's no surprise that when genetic drift is weak, it's the selection that wins out. It's what the balance of selection wants to achieve that is achieved by the model that we write down. So that is where I wanted to stop, having perhaps gone a bit too quickly through that last stuff, but I did want to show you something that we've been doing very recently Ian Letter, with whom that is joint work, is going to submit his thesis in the next couple of months. I have a very long draft sitting on my desk waiting to be read. But it's a really, I think, a really rather nice application of this probabilistic proof, which, although not trivial, is much more adaptable than the analytic proof to proving these results about, which are of genuine, I think, biological interest. So thank you very much for your attention.
Thanks, Alison. So let's give Alison a round of applause for the wonderful talks. Unmute and
I think everybody should be